All right. To for online folks, sorry, I forgot to record, but basically, um, what we did here, I only did the last two steps. So from yesterday's example, what we did was we used the added zero from the PD compensator to change the shape of the root locus. Changing that allows us to go through this purple point, which is the desired closed loop pole location. We found that by calculating the new settling time with this relation here. And then once we were able to do that, we then we use the angle criteria to determine where the zero needs to go in order to shape the root locus such that it passes through this desired closed loop pole location. Once we were able to figure that the angle of the desired zero, which is phi1 here, we then use this equation here to just find the zero. The nice thing about PID controller design is that since we're only adding poles and zeros on the real axis, we never have to worry about the vertical component here. We only need to find the horizontal component there. Once we were able to find that, we found the zero location, and then from there we use the magnitude criterion to determine the gain k such that the closed loop poles end up in the purple spot. So now I'm going to show you code this up in MATLAB, or I already have the code for it. I need to open up MATLAB, so give me a sec. All right, if MATLAB's going to open up or not. Really? Oh no. You know, the problem with streaming, recording, and trying to run MATLAB just takes up so many resources on your computer. And I have no patience. So I have opened MATLAB 4 times now, making my computer even slower. Well, while MATLAB is opening up, this is a PD compensator for an analog system. And basically how it works is we have this capacitor and resistor in series going through this op amp. So the reason why it's a PD is because it's using active electronics. The op amp requires electricity, and I don't have it drawn in there. Oh, it's opened up. All right. Oh my God. This is what I get for being impatient. Well, anyway, while that's loading. So then here, basically the input is voltage, and the capacitor will receive the full input voltage. And then what happens is the current through the capacitor changes proportional to the input voltage, meaning that this is a relationship. So then what's happening here is then when we measure the output, we're actually seeing the change in like what we see in the output. The size of the output is going to be proportional to the change in the input based off of this wiring. And it's going to be the negative because this is a negative op amp, but it doesn't really matter. You just multiply that by the negative number to get a positive output. And then so this passes through the resistor, and which causes a voltage drop, and that voltage drop is proportional to the derivative. And the output is still in voltage, but the voltage is proportional to the rate of change in voltage. So that's like a PD controller in an analog system. One cool thing about this, and I think I talk about it in a later lecture, is that PID was actually invented a century ago, and it was they designed it specifically to steer ships. I have no idea how they would apply that, but I thought it was pretty cool. Let me share my screen on my laptop once I open up the code for it. I'm not going to type it up today. I'll just run it. All right, I have a PD demo and PD demo complete, and I do not remember which one it is. This is from last year. Well, we're going to open up both of them. Let's see. Okay, that's lead. All I'll share my screen. Okay, so our original system had g of s is going to be 1 over, just to write out for visualization, s plus 4 times s plus 6. So here I define transfer function. Oh, this is a trick you can do. You can define the transfer function as s, but I don't think I use it. Oh, I do. Um, this defines the variable s as a transfer function. Cool thing about it, so if I do this little trick, MATLAB now sees s as a pole, or as a, yeah, it just sees it as a continuous time transfer function. So I do s plus 3 here, or s plus, I don't know, s plus 3, 4 divided by s plus 2. It will actually, oh, it will actually automatically create a transfer function right there. Anyway, little trick. So what we're going to do is first we're going to create our open loop transfer function. So this is our open loop transfer function. And then we're going to plot the root locus. And in my chat thing. Oh, thank you, Tom. It's very cool. I'm glad you think it's very cool. All right, so here our locus will tell you, here's our system. So they put the K here in the feedback. It's actually the same as just pulling the K out right here, because when we're defining the open loop transfer function, it's G times H. And in this case, H is K. And so it's still K times G here. And textbook has a slightly different definition. Here's our open loop transfer function. And it should plot soon. There we go. All right. So since we have 3 poles, we have asymptotes going off at 60 degrees, 180 degrees, and negative 60 degrees, which we can see here. And we have a damping ratio of 0.502, I believe. So that was our original point here. Our gain was 43.2, and we can see that this is under 16% because that was our original design parameter. So this is our open loop transfer function. So our gain is 43.2. So then to create our uncompensated system, TU, what we do is we take our open loop transfer function, multiply it by that gain, and then we create this closed loop transfer function. This is the uncompensated closed loop transfer function. 43.2 or 3 was taken, is the gain for zeta equals 0.502. So when I run this section and I use step info, instead of doing a step response, it actually just tells me the rise time, settling time, transient time. Let me minimize this. Feeding control. Settling max and percent overshoot. So we said 15, it was 15.8 based off the root locus right here, 15.8%. But in reality, it's actually 15%. It's a little bit lower overshoot. And the reason why is because this, in the root locus, this number we're seeing here is based off of a second order system. So if I were to remove this pole at -6, we would actually see a different value. Okay, so we actually just, so the value I grabbed was from here, which is going to be this value. This is how I calculated the selling time. So then from that point on, we found that the 0 is at 3.01. This is the PD controller, by the way. And then we calculated that our gain is 47.5, and we wanted to pass through negative 3.61 plus 6.193 J. So then we're just going to plot that right now. So you see now that this plot looks different from the original plot. So on the left here, it's usually like left side's the original, right side's the new one. So left side here, we have the original plot, root locus. And then on the right side, we have the new root locus. You can see the shape has changed. So since we added a 0 here now, this the breakaway point has been moved to be between -4 and -6 because of the real axis segment rule. We have a real axis here. And we're going to check if it passes through -6. So negative 3.61 is what we're looking for. And you can see how quickly the gain changes. And that's pretty close. Yeah, so 46.5 or 47.5, 47.3. You can see that this is basically the same point. Even the damping ratio is the same, 16% overshoot. Now, if you look here, you can see we actually have a closed loop pole as well along this point here at we're looking for a gain of 47.5. So roughly there. And we have a pole here and a pole somewhere down here at 47.5. I'll just move it close. So basically, these 3 notches here I have on the graph is roughly where our closed loop poles are. And we actually can't use second order approximation anymore because of this added 0, because we actually have a dominant pole, which is not complex conjugate closer to the origin. So this might behave more like a third or first order system. So we use second order approximation to design this, but it might not hold anymore because of that added pole. Because adding that or at that added 0, adding that 0 has increased our system order by 1. So what we're going to do is we're going to run step info and we're going to check the settling time. And we're trying to do a 3 times reduction in our transient time or our settling time, which is 3.4. And if we look at our settling time here, it's 1.1. So we're actually still good. So here our percent overshoot dropped even more. Even though we designed it for 16%, it's actually even lower. So that's why we actually run simulations to check our design. And we don't really ever design this by hand. We just do gain tuning on the computer until we get a desired response. But let's just do let's just compare the two. TU, I believe. T compensated, and then add a legend, uncompensated. And then we're compared to the PD design. Oops. All right, and we can actually see that our transient time is a lot faster. It's within 2%. It gets to that 2% a lot faster. One cool thing about step plots is that if I right-click this system, or I right-click this plot, I can click properties. I believe it's properties. Nope, that's property editor. It might not work for when there's 2 plots. Nope, that's not it. Somewhere here. So property inspect. Nope, system. Oh, characteristics. There you go. So I right click, I go to characteristics. We can click on settling time, and then it'll plot us the settling time. I can right click it. I can look at the steady state, rise time right there, peak response. It'll just plot all of it for you. Anyway, so this is a PD controller. One thing about this, since this system is already a type 1 system, it will have a 0 steady state error. But if I were to do a ramp input to the system with the PD controller might have a lower steady state error because the gain is higher. We're using a higher gain now. Are there any questions? All right, so we're going to go back to all right. Somehow I need to open up meeting controls. There you go. All right, so that's a PD controller. Now we're going to go to its to lead lead compensator, and lead compensators basically do what lead controllers do, but they're simpler to use but harder to calculate. So lead compensator is a passive network, meaning passive meaning it doesn't need electricity, that adds a compensator pole and zero and reduces the transient response time. So we add a zero and we add a pole. And the point of adding a zero and a pole now, I guess like this is how we model it for systems that do not have electronics. The main criteria for this to be a lead compensator is that our pole needs to be further to the left than our zero. So basically the value of P needs to be larger than the value of ZC. And the reason why is because we require this for something called phase lead. If ZC is bigger than PC, then it's called phase lag, and that's going to be covered in chapter 10. But this is something that we need for it to be a lead compensator. Because the whole point of a PD controller or a lead compensator is to reduce our delay. So reduce our phase lag or our delay. So that's the structure for it. It's just a pole and a zero. So then lead compensators are approximations of PD compensators, and it's the same thing, useful in improving transient response time. It's simpler due to passive network, which does not require a power source. It introduces less noise than the PD compensator because it's actually not taking the derivative of our error. And you want the angular contribution of the zero to be greater than the pole to improve transient response, and this is going to be covered in chapter 10. It's basically, this is what makes it a phase lead system. Hence the name lead compensators. You want phase lead in the system, which reduces the lag or the delay. And for this to occur, that's the condition. So then kind of like foreseeing the future, when we're talking about lag compensators, we want Z to be greater than P. And that's going to be in the second part of the lecture slides. So the design is it's pretty straightforward. Oh, let me talk about the effect. This is new. So the effect of it is that it also reshapes your root locus and moves your closed loop poles to the desired location. But I guess one effect I don't have on here is that because we're adding a pole and a zero, it is a lot harder to, not a lot harder, but it is generally a little bit more difficult to calculate by hand because you have to take the angle criteria for both the pole and zero that you have now added to your open loop system. So the effect is that it improves your transient response time. There's actually less noise amplification than PD compensators. So if your system's noisy and you have a noisy error, you actually won't get that amplification effect from a purely derivative controller. It's a passive system, so it's very, very lightweight. And it's not as effective as PD compensators because it's not a true derivative. And additional complexity may cause a second order approximation to be less accurate. This is actually kind of true for the PD controller, but the pole here that we have in the lead compensator will also complicate our design. So the steps are still similar, where you want to use second order approximation for your design. Then you pick an arbitrary pole or zero in the left half plane. So the reason I say pole or zero is it's up to you. You just pick one pole or zero to place. And then basically, once we do that, we evaluate the system performance at the desired closed loop pole location. Then, based off of that new desired closed loop pole location, we then find the complementing zero or pole to meet the angle and magnitude criteria. So basically, we arbitrarily put a pole down, and then afterwards, we then calculate the angle for the unknown zero location. And then from there, we place our zero there. Our root locus will pass through the closed loop pole location. However, if your pole is greater than your zero here, that's a lag compensator, which we don't want. So then we have, if that doesn't work, then we have to repeat steps 2 through 5 again. So it's a little bit more complex to design. I have asked lead compensator and lag compensator designs on exams before. So I'm not going to have you arbitrarily pick a pole location, then calculate a zero. Instead, what I usually do is I just pick a pole or zero location for you. Then all you have to do is apply the angle criteria and find the complementing pole or zero. So it won't be very open-ended. But on homework, it's a lot more open-ended. You generally want this to be true. And it is a little bit more tedious than PD controller design. So since it's not as effective, our constraints for improving the transient response time is a little bit more, it's a little bit more relaxed. So it's not as strict. So instead, we want to design the same system, but now with 30% overshoot or less and a 2 times reduction in settling time compared to under 16% and a 3 times reduction. So the steps are pretty similar up to that point. So what we're going to do is I'm going to draw the pole zero map again. And because it's higher in complexity, we do have 2 blank pages to work on it. All right, so let's draw the pole zero map. I'm going to draw it on the left side here. And this thing I'm drawing is just from MATLAB. I don't really have it off the top of my head, the values. So I'm drawing the root locus. We have pole at -6, open loop at -4, and an open loop at 0. And root locus still the same. Looks like this. We have a breakaway point, like right there. And basically, we're looking for a 30% overshoot. And 30% overshoot. And I wrote the equation in the previous example, so I'm not going to write it out again. Of course, so 30% overshoots corresponds to 0.358. So then we're basically looking for the constant damping ratio line somewhere here, where zeta is equal to 0.358 along this line. And make this line a lot longer because we want a 2 times reduction settling time, and we want damping ratio to be 0.358. So our closed loop pole is going to be right here. And this point here, and this is just found in MATLAB, is negative 1.01 plus 2.63J with a gain of 63.3 at that point. So then we're going to use second order approximation again to calculate the settling time. To find TS uncompensated. How did you find that gain of 63.3? That's just from MATLAB. I'm cheating. MATLAB. I just click on the point, find the find 63.3, and then yeah, you know what? I'll just, if we go back to there's actually one other thing I want to show you on MATLAB, so sorry to just jump back, but also to answer your question. When we go back to that root, because we're using the root locus of our original system, it's still the system here. One thing I do want to show you, I forgot to mention it, so that's why I'm coming back here. You see these little diagonal points? Those are your zeta lines. So you can see zeta is 0.2, zeta is 0.38, all the way to zeta is 1. And then this radius here is your natural, like your natural frequency where it's constant as well. So that's how you read this plot. And to answer that question, I just literally I zoom into this point here because we're looking at close of the poles. We're looking at, I think it was 0.358. So we see 0.3 and 0.42. So it's going to be between these two sector lines. And I just pick roughly where I think 0.358 is at, which is roughly there. Close enough. It's 63. And I guess like the other day I had a ton of time. So I was able to, or last year I had a ton of time. So I got to the exact value of 0.358 and it was 63.3. That's how I found it. So there we go. So I'm going to stop sharing that. All right. So now we have, so T settling time uncompensated is 4 divided by zeta times omega n. And that's going to be, so that's going to be 4 divided by 1.01 because that's the real part of the closed loop hole, which is roughly equal to 4 seconds. And we say 3.97 seconds. If you say 4 seconds, I'm cool with that. Because this is all approximations and it's not going to be exact. So then we want to reduce our settling time of the compensated by half. So it's going to be TSU divided by 2 for a 2 times reduction. Or is that a 1 time reduction? Well, anyway, you divide it by 2 and you get 1.99 seconds. And this is actually going to be equal to 4 divided by zeta omega n of the compensated system. So maybe to be more thorough, I should put a U here for the uncompensated natural frequency. And basically, to draw out, this radius here is where our natural frequency of the compensated system is going to be 5.63. So I calculate that because I just plug in 4 over 0.358 times omega n c. And I'll add more sig figs, 5.626 radians per second. So then basically, when we look at that root locus plot, we're looking at that constant natural frequency line, and we look at that intersection point for the constant damping ratio line, and that's where our closed loop pole will be at. So our desired pole location, desired closed loop pole is going to be at negative 2.014 plus or minus 5.2, 5.252J. I cannot read today. Complex conjugate pole, so there's 2 of them. I can find the root locus of evaluated down here if I wanted to, but usually I like to stick above the horizontal axis on the positive side. Okay, so then our next step is to, what I'll do is I'll move this down here, copy. Next step is to arbitrarily, and I know it's scary when you have the freedom to choose something on homework and it's open-ended. Arbitrarily pick ZC and solve for PC. Or we can arbitrarily pick PC and solve for ZC such that the root locus passes through negative 2.014 plus or minus 5.252J. All right. So one thing the textbook really likes to do, and if you want to do this, you're more than welcome to. I'll write it down in my notes, but I personally don't do this, is they like to pick a zero such that we have pole zero cancellation. So here we have 0, -4, and -6. I think what the textbook did in this example was it put a pole at -4, so we get pole zero cancellation. So then the angle contributions from the pole and zero cancel each other out. That's one less angle to calculate when we're evaluating that point. It makes this whole step a lot easier. I don't like pole zero calculation because it's not really feasible in real life, but in homework and classes, do pole zero cancellation. You're more than welcome to. It's a very valid way when you're just calculating these things by hand because there's no need to calculate extra angles. I know you guys all know how to take the arctan and add and do all this algebra stuff. You're not being tested on algebra. You're being tested on how to move the root locus. So I'm gonna write it down here. And it's the textbook's method. It's not my method. So don't come to me if you ever try to do pole zero cancellation in real life. Likes to use pole zero cancellation. It simplifies calculation. The only caveat with pole zero cancellation is that because we want this to be a lead compensator design, whichever pole you choose to cancel out, your zero still needs to be to the right of it. So it needs to be a smaller number. Simplifies calculations. And you can find this example in the textbook, but I personally did not use the numbers from the textbook. So I deviate from the textbook in this example. So instead, I choose ZC is equal to 5 to avoid pole zero cancellation. But the textbook, if you go to it, I think it's this example or probably the lag compensator example or the lead lag compensator example. They will do pole zero cancellation, but I didn't do that. So you have two different examples. And so here, I'm just drawing this out visually. We have a pole at the origin, pole at -4, pole at -6, and then now we have a 0 at -5. And then I don't know where this pole is going to be at. I'm just going to arbitrarily put it here. It doesn't mean it's between -0 and -4. We just don't know where it's at. So minus PC is right there. And then we're trying to evaluate it such that the angle trying to evaluate it at -2.014 plus 5.252J, such that our angles add up, meets the angle criteria, which then reshapes the root locus to pass through that point. So I'm going to call this one theta 1, this one theta 2, this one theta 3, this one phi 1, and then theta 4 for our pole. So we're going to apply angle criterion. So we're going to find sum of the angles of the zeros minus sum of the angles of the poles is equal to 2i plus 1 times 180 degrees. Theta 1 is going to be equal to evaluated point, which is 5.25. Minus the height, minus 2.014 minus the pole location. We can see this is a quadrant 2 angle. So we're going to be aiming for an angle that is greater than 90 degrees and less than 180 degrees. And it's going to be, in my calculator, it was minus 69.02, but we add 180 degrees to put it in the right quadrant, which is quadrant 2. Theta 2, I'm just going to write out the numbers now. Let's see, 5.252 divided by minus 2.014 plus 4. It's going to be equal to, this is going to be a quadrant 1 angle. So it's going to be 69.29 degrees. Theta 3. So 5.252 divided by negative 2.014 minus 6. So that's going to be plus 6. That's going to be equal to 52.8 degrees. And then now we also have phi. And we get 5.252 divided by negative 2.014 minus 4, so plus 4. Oh, no, sorry, plus 5. Minus 5. That's going to be equal to 60.38 degrees. So then we can apply, so we apply the angle criterion to actually, let me specify the step to find theta 4. So then we get phi 1 minus theta 1 plus theta 2 plus theta 3 plus theta 4. So it's all the angles of the poles. It's equal to an odd multiple of 180 degrees. I'm going to plug all these numbers in. And we basically get, after some heavy rearranging, we get 180 times 2, or I'll do 2i plus 1 multiplied by 180 degrees. Minus 172.69 degrees. And in this case, I'm going to choose I is equal to 0. So then we get this really, really shallow angle. And the reason why we want a small angle, we want theta 4. We get, so I choose I is equal to 1, and we get 7.31 degrees. And this is good because we want phi 1 to have a greater angle than theta 4. It implies that, but in quadrant 1 though, this is for quadrant 1 angles, because this implies that the pole is to the left of the 0 now. Did I do that? Wait, no, sorry. No, I wrote that in reverse. We want theta 4 to have a really small angle compared to phi 1. That's what we want. We want quadrant 1 angle. We want theta 4 in quadrant 1 to be larger than phi 1. Yeah, I was right the first time, man. I'm just, oh my, even with my coffee. Yeah, that's good. And now that we found that, we're going to pick this up on Monday, but basically the next step is to then find the location of our pole. And then once we find that, we then go back to root locus, get the gain, or we apply the magnitude criterion, then we get the gain. And then once we get the gain, we then plug it back into the closed loop transfer function and we simulate to see if we achieved that. So we'll pick that back up. We'll pick up on that on Monday. Have a good weekend, and I'll see you Monday.